All right, thank you for attending Optimization and Debugging. Our first speaker, Optimization and Profiling.
No, it's Profiling and Debugging.
Profiling and Debugging, sorry about that. This is John Kaz, our speaker. He's our first speaker, and then Carlos will be following up with profiling.
Good morning. So first we're going to talk about debugging, primarily debugging tools. Here's a quick outline. We're going to talk about two tools that we use quite a bit here at TAC, GDB and DDT. I'm going to run through the basics of each tool, and then we're going to have a short lab where you'll get to play with the tools. Although I'll warn you, if you want to use DDT, you need X11 support. Okay, so what can you do with these tools? GDB is sort of the backbone of debugging. DDT actually sits on top of DDT sits on top of GDB to do most of its debugging. But since DDT has a much richer interface, in general, for heavy debugging tasks, I'll use DDT and save GDB for quick and dirty operations. And I'll cover the basic use of GDB and a little bit about how to attach to a job, because that can come in very handy when you have a job or an executable that doesn't appear to be doing anything but doesn't stop. With DDT is a distributed debugger, and this is what we use to debug problems with MPI or multi-threaded codes. And it works well with our scheduler and our systems and all types of MPI. Okay, why do you want to use a debugger? Does anybody write perfect code? I don't. Oh, Carlos does. So if you write code, you're going to have bugs. Even no matter how much you stare at the code and think it's perfect, I invariably have a bug. Even when I did the lab for this training, I thought, oh, I've used this code many times. It works. No, I still had a bug. I had to fix it. So you're going to have bugs. And if it's a bug that's beyond just a simple print, see the data change, it's nice to have a debugger. And also, the point about the buffered output is that when you're printing output, what you see printed to the screen may not be what's happening in the code. Output is buffered unless you're printing the standard error. And so where you think you are in code execution is different. This is where a debugger is really nice, because if you want, you can step through the code line by line and look at each execution and how your data is changing. Okay, so GDB. GDB is the GNU project debugger. GDB lets you do many things that are convenient when you're debugging a program. You can start your program, you can tell your program to stop at specific, what we call breakpoints, stop at specific lines. You can examine the data in your program in the middle of a run. You can also run a program until it crashes, and GDB will usually tell you where it crashed and on what line it was at. If there's a core file, you can sometimes attach to the core file also after a program has run and see what happened. And you can do a lot of these things even if you didn't compile with debugging. Although usually after it crashes, you have to go back and recompile with debugging so you can examine the program in detail. And this is an iterative process with the debuggers. You run the debugger, you look at the code, you figure out what's wrong, you change something, you recompile the code, you run the code again in the debugger. So, throughout this, I'm probably mostly going to mention the Intel compilers. Those are the default compilers on our system, but we also have the GNU compilers. And in general, everything I talk about works for GNU and Intel with one exception, which I'll get to in a little bit. When your code has a bug and you debug, the first thing you want to do is compile without optimization to see if you still have the bug without optimization. Because sometimes when you compile with optimization, the compiler gets a little aggressive and might introduce a bug into your code, or maybe just something the optimizer does creates a problem. So first you want to run it without optimization. That's O0. You're turning off all optimization. Then the -G flag includes source line data. So when you run with the debugger, it can connect a line of source code to each execution. And I don't have a laser pointer, so I'll just use the mouse. The -D, a lot of times you may be running in a directory that's different from where you compiled, and the debugger may not be able to find your source code, so you'll just have to tell it where it sits. Also, help is important. The help for GDB is pretty decent. And once you enter the GDB prompt, you can type help at any time and help in the name of a command, and it'll show you the details regarding the command. So, how do you use GDB? In general, you use it, you start your code, you just run your code and see where it crashes. Sometimes you'll run it, it'll crash, you'll type where, or list the line that it crashed on, and it'll be obvious. Oh, I'm dividing by 0. I shouldn't do that. That's great. A lot of times it's not so straightforward. You'll look at the data and the data makes no sense, and this is where you have to go back in and sort of trace back all the way to where the problem initiated. And so when you get into a situation like that, that's where you're going to start setting breakpoints. You're going to start looking at data as the code progresses before it gets to the point at which it crashes. Okay, so here's a list of the basic commands in GDB. And these will be repeated in DDT, but in a GUI form with buttons and sort of a nice, easy way to use. So the first one, run. When you load a program with GDB, it immediately puts you at the prompt. It doesn't start running right away in case you want to set breakpoints or watch variables. So to start the program once you're in GDB, you type run or R. I think almost all of these commands have a nice little one-letter shorthand version. Continue means it will restart the program from wherever you stopped and continue until the next breakpoint, the program ends, or the program crashes. Now, step is one of the important ones. When you're in an area that you think the problem occurs, but you don't want to set a breakpoint for every line, you can use step to step through the lines of executable. So you're walking very slowly through the code. Now, if you have a large code or you have a bug that appears, say, only after 10 minutes of running, you don't want to just do this to the whole code. I mean, it's incredibly slow. But once you're in the area that you know it happens, so let's say you know it crashes at line 1000, so you set a breakpoint at line 900. And then let's say you know it happens on iteration 500. You can also set a conditional breakpoint, so let's say it stops on iteration 500 at this line. Then when you get there, you can step through slowly till you get to the point at which it crashes. And as you step through the code, you can look at data. You can look at your variables with the print command. This will show you the source code as long as you compile with -G. If you didn't compile with -G, I don't think list will show you anything but where you are in the stack trace. So break is how you set a breakpoint, and you can watch a variable name. And the where command, when I use GDB, this is probably the first thing I use. Because if I know it's going to crash, I load it up in GDB, I run it, and it crashes, and then I type where. And where tells me what line number it crashed on, where in the stack I'm at, and I can move up and down the stack with the commands that I don't have listed here, but up and down. And so I can see where in my program the problem was. And then if you type list, it'll list that line and some lines above and after the problem and give you some context. So this is sort of the first thing that tells you, this is where it crashed. Let me look here. Let me see if the problem's obvious. And a lot of times with GDB, that's as far as I go. Because if it's more complex than that, then in general, I run the code under DDT. DDT supports parallel codes, multi-threaded codes, and serial codes. It's just a nicer interface, and it's easier to look at the data. So here's an example, and this is the one we're going to use in the lab. It's just a simple program that's guaranteed to crash. When you divide by 0, bad things happen. And there's a C example and a Fortran example. Here's what you'll see when you run it. So in our lab, you're going to do this, and then you're just going to walk through and print some variables and just get familiar with the basics of GDB. So as I said, it's a divide by 0 problem. This is one of the ones that's simple to see. You type where, you look at it, oh, look, there's a division with X and Y. If I print X and Y, I bet they're equal. So you see that, then you can immediately go back and fix the code. Now, you can use GDB with C or Fortran. There's a little bit of difference in the way they access the arrays because Fortran and C store their arrays differently. And GDB is primarily designed for C, it's GNU. Fortran, to me, appears to be an afterthought. And that shows up because on our systems, if you compile with iFort and you use GDB to debug a program with the standard system GDB, you can't print any of the variables. They can't find them. They don't show up. There's some disconnect between the way Intel creates the executable and stores the debug data and the way GDB wants to access it. It works with gfortran, but not with iFort. Now, apparently DDT has a modified GDB in their stack that actually works with this. So if you really want to use GDB to debug iFort compiled codes, we can show you how. And so notice here, you can print vectors, you can print elements of vectors, you can print vector links like mini variables. You can also index. Notice that for C, indexing is with brackets, and with Fortran, it's with parentheses. But again, if you have a large array, it's very hard to look at the data this way. This is where DDT comes in handy. So for breakpoints, so the easiest way to set a breakpoint is just break at the name of the source code, colon, and line number. Now what this means though is every time the program execution gets to this line number, it's going to stop. And so if you got a bug that appears late in the program, you'll want a conditional breakpoint where you can add some sort of if statement that says, if this variable is greater than this, or if this variable is equal to this, then stop. Oh, the info command is useful. So if you've been fooling around and setting breakpoints and you can't remember what you've done, you type info. It'll show you all the breakpoints you've enabled. You can also enable and disable them. You can delete them. You can clear them. But again, I recommend if you're on our systems and you're debugging and you're to this point, I'd recommend you use DDT just because you've got a graphical interface that makes it a lot easier. And I'll show you that later on, where it's pretty much point and click. Okay, here's another way that I use GDB, one of the primary ways that I use it. I start a job on Stampede. The job starts running and running, and there's no output. Where's my output? What's going on? But the job doesn't fail. So I want to see what's happening. GDB lets you attach to a process, and when GDB attaches to the process, it will halt it. And basically when it halts, then you can type where, and it will tell you where in the call stack it is and in what program it's in. Now, a lot of times it may be buried in some library and you'll see some strange looking function name that's either an MPI function or an MKL function or some sort of internal function to a library. And what you'll do is you'll walk up the stack. You'll just type up, or you'll look at a list because it'll give you a stack tracing until you get to your part of the program so you can see where this call came from. Okay, so very quickly, how you do this is you have to log into the node where your job is running. And for this, you have to use the SQ command. ShowQ won't show you this. SQ will show you a node list of where your job is running. And the node list is in the order that the tasks are set out. So the first node will be the head node. And usually you can log in, use top to find a PID that's part of your program, a process ID, attach to that process, and try to see what's going on. Now, 9 times out of 10, if your MPI program isn't progressing, it's in an MPI call somewhere. There's a deadlock. 2 things are waiting to communicate are both sending instead of receiving when somebody should be receiving. And so, in general, what you do is you attach to a process. You look at where it is. Get out. If you're running more than one process on that node, you can attach to another process, see where this process is. And sometimes you'll see them hung at different places. Like if you see one hung in a barrier and the other one's hung in a send, this is not going to finish. You know you've got a problem. You know you've got a deadlock. Sometimes you might log in and see all the processes, but say task 0 hung in the same place. And to determine which one is task 0, that's not quite as easy, but in general, it's the process with the lowest PID number. In general, it doesn't have to be. But this is a good way to see that your program is hung. Now, if you attach to the process and it's at a certain part of execution, you detach. You quit GDB, and it'll ask, do you want to detach from this process? You say yes. Then you attach to the same process again. And it's at a different point, then it's not hung. It's doing something. Now, it could be in an infinite loop, or it could just be progressing very slowly. So if that's the case, you'll have to do a little more investigation to determine what's going on. But every time you run a job on Stampede, you can SSH into the node. So that's why you use this command to get the node list. And once you get the node list, you can SSH into the node, run top, and directly attach to the process. DDT allows you to attach to processes too, but it's a little bit more difficult. So if I'm using DDT, I just restart the job and run everything from DDT. Okay, so for now, that's all I'm going to say about GDB. We're going to have a short lab where you'll get to play with it. But in general, compile with -G and O0. That's your first step for debugging. And then you can run GDB and walk through it. A slide I left out of here that I just realized this morning wasn't in this deck of slides. There's a way to compile with trapping. So you can trap floating point exceptions and traceback. And sometimes this will save you a large amount of time because it'll tell you exactly where you introduced an AND or an infinity. It'll tell you the line number. But also when you run the debugger, it looks for these floating point exceptions and it should warn you. Okay, so now we're going to talk about DDT. DDT stands for Distributed Debugger Tool. It's a tool from Alinea and it's designed to run on clusters. That's its primary purpose, to debug MPI and multi-threaded codes, or hybrid codes that are MPI and OpenMP. It's also set up so that it's integrated into our scheduler, so you can use it with the scheduler. It adds some features that I don't think are available directly in GDB, but memory checking, it can show you memory use, it can help you look for memory errors maybe before you segfault and cause your code to crash. As I said, it's got MPI and OpenMP support. It's got a data viewer, which comes in handy because once you're dealing with large arrays, using print from the command line is very difficult. And so a lot of times you'll end up printing max val or min val of an array to try to figure out what went wrong. Because if you look at a tiny section of the array, all the data might look right. And especially if you have tens to hundreds to thousands of tasks, it's really hard to determine which task has a bad value in the data array. Okay, so when you start DDT, this is what you'll see. You'll see this splash window in the background, but if you start it with an executable, in general, you can just ignore this window, and you'll see the run window. And this is where you set everything up. So notice your program name will be up here. If there are any arguments to your program and you didn't include them on the command line when you start it, you can add them here. In general, you don't need to worry about the working directory. We have a parallel file system. That doesn't have to be set up unless you want to debug on the mic, and that's a different course. That's a little bit more advanced. You don't have to worry about IB run arguments. So what you'll do is you'll set your processor, you'll set some of these other settings, which we're going to walk through. And then when everything's ready, you'll hit submit, and it'll submit a job to the batch queue. And so this runs on the login node, and you'll have a GUI running on the login node that's forwarded back to you through it. It will start the job to the batch script, and once your job starts, it will attach to your processes. Now, before I go on, I want to say one thing about you don't have to run it through the queue, but if you don't run it through the queue. You can run it interactively through an IDEV session, but only in the development queue and the viz queues because it requires X11 locally. And those are the only queues where we have X11 installed on the local compute nodes. So sometimes I run it that way if I know I'm going to be starting and stopping a lot of times and recompiling, just because it's more convenient. I don't have to go to the batch queue every time I change the job. Okay, so since you are running from the queue, with your default setup, the first time you have to set up a project. Before you can submit to the queue, this project entry is empty on purpose. So a lot of you may not set a project in your batch jobs because if you have one project, you don't have to, but for DDT, you'll have to set a project. And so to get here, that's this parameters button. And the first time you bring it up and you set a project, it'll remember that. So the next time you run, it should already be in there by default. You shouldn't have to set it again. This other thing, if you leave this at 0, it'll use whatever the default number of nodes is. So if you ask for 32 processors, 32 tasks, and you're just running 16-way, which is the default on Stampede, it'll give you 2 nodes. If you want to run 32 tasks, say on 32 nodes, then you should change this to 32. Then you'll be running 1 task per node. But if you're not changing the number of tasks per node, you can leave it at 0, and it'll just calculate the number of nodes that need to be run. Okay, once your job starts up, this is the primary window. This is the window that shows you basically all the data you're going to look at. So sort of here in the center, that's your source code. What will happen is once you start, DDT will automatically stop at the first line past MPI init, the first executable line. Now, this is good because it gives you a chance to set breakpoints or watch variables or do whatever you want. Now, in a way, this is bad because DDT does this automatically for each MPI program. So if you have a program that does a lot of stuff before MPI init, and there's a bug there, it'll probably crash before it gets to this point. This doesn't happen too often, but every once in a while we'll get someone who has a ticket and they're like, I can't get DDT to work. Nothing. I bring it up and it crashes before anything shows up. And usually it's because the crash or what they're doing happened before the MPI init. Okay, so once this is up, you see I say process controls here. What this is processes. So by default, the focus is on all the tasks. So they're all grouped together. So if you use any of the controls up here, play is basically run, the pause is stop. So while it's running, you can just stop it. This little arrow with the into, that's step into. What that means is if the next line is a function call, it will step into that function and let you step through the function. This regular arrow here, that's just like the step function in GDB. It'll just execute the next line. This arrow here, up and out, that basically says if I'm in a function, go to the end of the function, go to the next level up, and stop. So these buttons are very convenient for stepping through an executable and going through quickly. Let's say you get into a routine, you're like, oh, I know the problem's not here. You can quickly go to the end and go up to the next level. Now, like I said, in the default focus, this happens for every task, every thread. Now what you can do is you can change the focus to process, which I really wish they'd use the word task because it's really task. Because when you focus on a task, if there are multiple threads for that task, it includes those. So when you focus on process, you can choose any one of these tasks, highlight it, and then you can stop and start just that task and its threads. And so you see thread here too. So you can go all the way down to the thread level. And so for one task, you can stop and start individual threads. But I'll warn you, when you start doing this with different tasks, you can get your program into a kind of a strange state because it's not really running in lockstep anymore. And so you'll get to a point where one task is waiting because you forgot to go back and start all the other tasks. So in general, I try to step through all the tasks together. And when I set a breakpoint, I set it for all the tasks. Now, sometimes you'll have breakpoints that are in if-else blocks. And so some tasks may not enter that and stop. And so they'll be in a different section and they'll keep running. And what will happen is when you hit the breakpoint, you'll see here this task list. The ones that stop will turn red. The ones that are still running will turn green. And so you may go, huh, I thought they would all stop here. And so what you can do is, if your focus is still on group, you can come up here and just press the pause button, and it will halt all the tasks. And then you can go to one of these tasks that were green and try to figure out, where was this guy running? What was going on? Okay, and so over here, this is the variable pane. Anytime you stop on a line, by default, it'll show current line. It'll show the variables on the current line. Now, if you notice, there's some tabs up here at the top. I hardly ever look at current stack, but you can look at locals. And what locals will show you is all the variables local to that function or subroutine. And so if you click on that, it'll be a much longer list, but you can scroll through and see. Or you can leave it on current line, and let's say you want to know the value of a variable. Let's say I stop down here and I want to know the value of I. So I can click on the do loop and it'll show me those variables on that line. This is an evaluation pane. So if you want, you can drag variables from here into here. And what it'll do is every time you watch, well, it's like a watch. Every time you stop, it'll show the values of those variables. Now, if it's an array, you'll either have to expand it or use the array viewer, which I'll show you in a second. And down here at the bottom, you've got several tabs. So in general, when you run and you stop, by default, DDT is going to show you the stack tab, which is the stack trace. This shows the trace of the functions that you've called, all the way from, say, your main program at the top down to whatever library, subroutine, or function you've stopped it. And you can move up and down this trace, whoops, much like you can move up and down in GDB, typing up and down. It'll show you the whole list. And it'll show it for all the tasks that stopped. So you can see, hey, some tasks are stopped in this routine. Other tasks are stopped in that routine. You don't know which ones, but it'll show you how many. Also down here, first is input output. So if you want to see the I/O, you click on input output, and you can select by task or have it show you the output for all the tasks. The breakpoint tab, I think that's the next slide. That will show you all the breakpoints you've set. And so to set a breakpoint, you would come to a line number, right click, I don't know what you do on a Mac, whatever. Right click and set the breakpoint. I only have one button. Right click, set the breakpoint. Right click, set the breakpoint. As you see down here in this breakpoint tab, it shows you what you set. It shows you it's for all processes, all threads, what line number, what function. And if there are any conditions or triggers, there are none. And what's nice is you can set these, and then you can turn them off without removing them. So basically disable the breakpoint. And then let's say you get to the point where, hey, I need to look at that again in the execution. You can stop and re-enable the breakpoint. Also, if you want to look at different variables for different tasks, you could come up here at the top and click on the different task, and then look at the value here, or you might have a variable in the evaluate window, which is basically a watch. And so you can click among the different tasks and see how the variables change. There's also an array viewer. This comes in very handy because, yes, usually if I'm running on a cluster, in general, I have a decent amount of data that I can't just print out. So I want a quick and easy way to look at this data, look at these values, and analyze it. So you can open up the array viewer, although notice here, I mean, this isn't that helpful. There's 25,000 values, and it's just listing them out one by one. I rarely ever look at something like this in detail. If it's really huge and I want to look at the data, there's a visualize option that can do, I think, 1D and 2D. So it can do a surface map of a 2D array. For 3D, you basically have to choose what you want to look at. But in general, what I do when I want to look at an array like this, I just want to see what's in it in general. And there's a statistics tab here. It's very helpful. So you can look at this and you can see the range. You can see the min, the max. You can see if you have any nans or infinities or negative zeros or positive zeros. Or no, this is the negative numbers, zeros, positive numbers. But in general, I look here just to see, do I have nans or infinities, and are my min and max what I expect? Do I see a really huge number? Because that in general means you've got a floating point error somewhere. Do I see a negative number when I shouldn't see any negative numbers? Okay, you can also look at memory usage through DDT. Under the Tools menu, there's a memory usage window that you can bring up. And so once you're at a breakpoint, you can bring this up and see the amount of memory each task is using. So this comes in very handy if you've got a program that seems to run okay for a while, and then it just seg faults. But you log in and look at it, and it looks like all the memory's fine. And so what could happen is you've got a memory leak. So you could run in DDT and stop it at various points in the program and see if the memory footprint's growing or if it's steady. If it's steady, then you've got a seg fault for a different reason. And we get questions all the time. Well, my program ended. I don't know how much memory it uses. We tell them it's seg faulted, you ran out of memory. And they have no clue how much memory they're using. So, in summary, this is how you start with DDT. You have to log in with X1140. There's a way to do this also through VNC if you've ever used VNC. We have a sample VNC script on Stampede. You can use the batch job to get a VNC session on a compute node in development or viz. But in general, I use it with X11. Now, if you have a slow connection to Stampede, this is pretty painful. Luckily, from my house, I have a pretty good connection, so I can use DDT from home without much effort. So compile your code with -G-00, just like with GDB, and then you have to load the DDT module. If you've never used DDT before, it will set up everything for you except for the project. And you can get going pretty quickly. We'll do that in the lab in a second. To run it, just DDT in the name of your executable. If you have any arguments to your executable, you can just put them on the same line. And it'll auto-populate them in that window, so you'll have your executable and then your arguments. If you're already in DDT and you want to change the executable, you can go to the run window and change what you're running. And we'll go through this in the lab. Okay, so when should you debug? Well, if your program doesn't finish, yeah, you should probably debug it. If your program is erratic, so let's say you run the same thing twice and you don't get the same answer, and you don't have some sort of random seed that would cause an answer to be different. Let's say you run it and you get wildly varying performance. That could be something you need to profile, but it's probably a bug if the performance varies, say, by a factor of 2. Something strange is going on. And the hang, well, this is one where you pretty much have to debug it because you're never going to finish. And yeah, if you ever see nan or infinities in your output and it's a variable you don't care about, you need to debug it. You shouldn't ignore that, because a nan and an infinity, it's like a virus. If you get one, every operation it's in, every other variable it touches becomes a nan. And so it will propagate throughout your code. And what you see in the output is just the end result of that. You need to debug it to trace it back to find out where it began and prevent it. Okay, so I still use print too to debug. If I've got a simple code and I think I can compile and run fairly quickly, I'll just keep adding print statements till I see the problem. But in general, if it's not a code I developed, or if it's tens of thousands of lines, I just start with the debugger. It's easy to use. It helps a lot. Okay, so now we're gonna get started with the lab. So, escape, 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 escape. Quit PowerPoint. I'll just open the other one.
Yeah, that's fine.
It's over here on the side. So I think it's under this debugging.
This is your lab.
No.
This one?
Yeah, that's Carlos's. This one. The name's underneath. That's it. Oh no, that's the lab. You're right. This is the lab.
There you go.
Okay, we're gonna walk through the slides, and then you can get started. Then after about maybe 10 or 15 minutes, I'll walk through it live. It's pretty short. And I've got something wrong, so I'll have to change my instructions a little bit. So first, you have to log into Stampede. Everybody, well, for this part, you don't need X11 for GDB. You only need that for DDT. But if you got X11, log in with CapX. Untar the files. Go into the directory. And here's the part that's going to change. Compile before you do your IDEV session. I forgot that the compilers are not available in the normal queue where our reservation is. So you need to compile on the login node. You can compile the C code or the Fortran code, although if you compile the Fortran code, as I said before, if you try to print the variables, you'll get a strange error message that'll just complain about not being able to resolve a 4-byte int. Everybody on Stampede, at least? Yes? Okay. Once you get on, you can run the code. So I'm going to Guess X Windows doesn't look that great on Mac. What's it doing? No, it gave up. Has anyone been able to get in with iDev? Yeah? Maybe I'm not in the reservation. I can't find Scratch. Okay, login 2 has a problem. Pity one's on login 2. Log into one of the other login nodes and you'll be fine. So if you've run this, ignore the debug info, but you see GDB tells you, hey, you had an exception, it crashed. If you print X, print Y, see obviously Y. So you can list, see the line numbers, type where, see where you're at in code, see the stack trace. D, you know, 17, 9. Yes, restarted. Print X, print Y, continue, Y, continue, Y. That's how you can step through a code and see what it's doing. If you compile with ifort, just to let you know what you'll see, you'll get this error reading variable. GDB doesn't work that great with the Intel compiler. Although, as I said, there's a version buried in the DDT stack that does work because DDT sits on top of GDB. That version works fine. Okay. So now, surely you've moved on to the DDT portion. So before you start the DDT portion, you must exit from the iDev session. Then you can compile the deadlock example, either one, the Fortran or the C, load the DDT module, and start DDT. And once you start DDT, you should see the run window. Anyone has any questions? It's fine. Yeah. So the problem will be if you use -G in one of the optimizations, where you stop in the code, where you set your breakpoints, may not be exactly at that point in the execution. So for O1, it's probably pretty safe. For O2, it's going to be a bit more aggressive. For O3, it's going to be very aggressive. And so it may reorder loops, may split loops, may do loop unrolling. And so in general, you always start at O0. And if the bug disappears at O0 and happens with one of the optimizations, then you can walk through the optimization. And then a lot of times you're looking at variable changes and data changes to see where things go awry. Okay, so one of the things I want you to note if you're in the DDT section is we've set the default type of MPI you use to Vapage 2, but you can use DDT with basically any type of MPI. We also have installed on Stampede Intel MPI. We have some people who use their own version of OpenMPI. So if you're going to use DDT to debug and you're using a different version of MPI, you need to select this change button here, and it'll bring up this window, and you need to change the implementation. In general, you shouldn't need to change anything else on this page, but each of the versions of MPI have different signals, and so DDT has to know what signals they need to trap and catch. Also, you can change the number of processes. If you notice here, I say set it to 8, but in my picture, I think I have 2. Either one with the deadlock example will work. Turn on memory debugging. Memory's not really an issue with this simple example, but what I want you to take from this memory debugging pane is, by default, we set the memory debugging library to be C Fortran with threads. And in general, I found that works for threaded and non-threaded. But if you're using C++, there's a drop-down menu, and you should choose C++ with threads. Because if you use this library, sometimes it will cause errors, or sometimes it will cause DDT to crash because it's not expecting however C++ allocates memory. Also, I've heard of a few cases where people had to add guard pages to prevent DDT from crashing when it was trying to do memory debugging. So what guard pages do is it adds an extra buffer of memory allocation. So if you go outside the area that you allocate, there's this buffer that, and DDT will detect that you're writing outside of what you allocate. It's kind of similar to if in Fortran you can compile with check bounds, Fortran will check to see if you exceeded the bounds of your array. Is it not starting?
It's got the flash number.
Should start. Since we have a, well, yeah, I need to do that. So in the past, I had problems with the license service. People accessing it. Anybody else have problems with DDT handling? Startup? No?
API class.
You can type it. Sometimes they do it when you switch the methods. Because you can see this AT connection, I would just switch the method. so you're right. You're going to go to all the windows. I think Windows on top. So something else I've added just for this lab, this batch submission. Normally, you shouldn't have to touch this in normal use of DDT, but since we have a reservation, I changed the template file that it uses. And also, you know, I forgot to mention this, but if you use this, when you run again on your own, you should change this back or just remove your .alinea directory and it'll reset everything to the defaults. But I set up a special template file for this lab, and what you do is you change to that one, and what it adds is this Slurm reservation, so you can get in right away. Otherwise, you just get stuck in the normal queue and fight it out with everybody else. And this is a feature I got to think about how I can add to DDT in general, so that if you have a reservation.
Is it okay to use dash line or do you use dash?
Dash line is
I'm not.
fine. Dash line is just a little bit more optimization. Handshaking with the dash arrows. It can encrypt the stream too. Once your job starts, you should see a window like this. It won't go, if you use the reservation, it shouldn't be up for long because Slurm should pull the job in within 30 seconds to a minute. But this is just when you run normally and you queue a job up with DDT, this is what you'll see. And once it starts, you'll end up right past the MPI init statement. Then as you can imagine, with a name like Deadlock, the program's going to hang. No? It worked for you? Well, it should hang. And so what you can do is just stop it, see where you're at. When you get to this point, it's about as big as I can make this window on this slide. But one task is at one place, and the rest of the tasks at a different execution line. And if you look at each one, you see they're both calling MPI send at the same time, and MPI send is a blocking call. So if nobody's receiving the data, then no one can continue. And this is a fairly simple case, but one in which it would be very, very difficult to debug with multiple GDB debuggers. Whoops. Yeah. That's in Vapage 2. So for Vapage 2, MPIF9 and MPICC, the compilers are just shell-script package. And you can type MPIF9-show, and it'll show you the actual compiler. So you'll see IPM, what libraries are linked in, what include files, and all of that. For Intel MPI, the compiler is actually designed to Intel modules.
Guys wrote those.
No, this is part of the Vapage install. So you install Vapage with this. A lot of times people will try to install software on their own, and if it's older software, it will say, oh, you need to put your MPI libraries here, your MPI files here. But no, leave all that blank. You just set your compiler to the MPI line. And then they can't involve it. Okay, so I can come here. Set this. Okay. So this was what I was talking about earlier, C++ and threads. And if you're on the memory, if you're using C++, you should select this if you're doing memory debugging. Pages. Okay. Submit. Yeah, stay off login too. Has anyone been able to get the DDT part to work? Something about this Mac and logging in. I don't end up with a scratch environment variable, and then it drops me. So I had to bounce from login node to login node. Now I think I've got something that works. Although I'm in development. That's right. They have to change it to normal. But it was X11 problems. That's what X11, and for some reason my dot files didn't get executed correctly when logging from the Mac. So then I just jumped to another login mode, formal login mode, and then that didn't look good. Okay, finally. If anyone's still watching, or if they haven't done it yet, it's hung. Stop. Notice I'm buried down in some MPI code because the debug information for MPI is in this library, and it's hard to make sense of that. So what you can do is just go to the top of the stack. See, for one task, I'm at this MPI SIN, it's task 0. Then let's say I want to come down here and look. The other task, see, it moved me, when I clicked on this, it moved me up here to the first task where this was stopped, task 1. I can click on any of these, and they'll all be at the same place. Come here to SIN buffer, see all my values, view array. I have to click evaluate to actually see the data. There's the data. Let's visualize. Oh, it's a plane. Check my statistics. But here I can easily see in my program, processor 0 is sending, and all the other processors are sending, or all the other tasks are sending. And so it's a deadlock. Nobody can continue until the send completes, but no one's receiving. So you can fix it just by reversing the order. Also, something I'll show you that's pretty useful when you're running through the queue. If you just want to rerun the program without compiling it, you can go to restart session. It'll restart the whole session without submitting another batch job, so you don't have to wait in the queue again. And so now you could come down and you could set breakpoints. And notice when it stops, hits the first breakpoint, it asks you, do you just want to stop for where the breakpoints were, or you can pause all. So everybody stops. Click on the different processes, it puts you at the current breakpoint for that process. Here's input output, it's stuck on output for 0. You can go down 1, it shows output for all. You can change it for individual tasks. There's a list of the breakpoints. I don't have any watch points. Here's the stack trace. Because I haven't entered into the library yet, there's only one level. Tell it to go. Stop. Any questions? Okay, we're going to take about a 15-minute break, 10-minute break, then Carlos will get started. Thank you. Oh, I'll tell you one more thing. To reset, if you're ever in DDT and things have gotten kind of screwed up and your settings are messed up, because I just had you use a specific template file, you'll want to reset that. The easiest way to fix it, remove this .alinea directory in your home directory. That's where everything you've done, that's where it's saved automatically. So if you just remove that, the next time you start DDT, it'll start up with the default configuration. And yeah, I screw this up all the time, so I do this a lot. Bring Carlos's up. I think Carlos has. I haven't.
So maybe planning to update the whole software stack needs to be pushed sometime now. And probably based on the latest and ops too. I don't know.
Should I put time?
And then we go with the dialogue. So how to follow it.
All right, so it's 10:30, so we'll start moving on with the profiling part. Most of what I'm gonna be doing is giving you a brief, and by brief I mean about 60 seconds introduction to optimization. So I'm just gonna talk a little bit about the optimization process, and I'm gonna use that to introduce all these profiling tools. I'm gonna start with very basic tools. Some of them are easy to use, but they give you a very limited amount of information about the performance of your code. And then I'm going to go to slightly more complicated tools until we get the most complex to use tool you can use for profiling. I'm not going to do exercises because there's a lot of material here. I would like to be able to cover most of it. And essentially my intention is to show you what tools we have available at TAC and give you a brief introduction on how to use them, but not going very deep, because most of these have actually a nice graphical user interface where you will find that most things are relatively easy to do. And when they're not, I'm going to have a couple of screenshots to show you why. First of all, the optimization process is very similar to what John described before. It's an iterative process. You can always continue optimizing your code. The question is, at what point are you going to stop and decide this is enough? You know, I need to publish papers. I don't need this code to be 5% faster. So what you have to do is decide how far you want to go with the optimization process. If you can get your results in 12 hours, maybe that's enough and you don't want to touch that code anymore. You don't care that it can be further optimized. The critical part about optimization is to identify accurately what are the hotspots in your code. And for that, most of the time, you need profiling tools. Once you identify these hotspots, you're going to try to compensate for them. You're going to try to fix them. You're going to introduce changes in your code. Don't assume that the new code is going to be any faster. You might have just moved the hotspot to a completely different place in the code, to a completely different type of problem, and your code might be even slower than before. So remember that you always have to test after you make any changes. Profiling tools are the critical tools you need to use to identify these hotspots and be able to do anything about code optimization. Now, it's not only about the tools, it's also about the way that you perform your optimization. And in this case, control is basic. It's the most important thing you have to do. If you run a code once and you got some result, and you use that as a basis to establish that that's your code performance, you might be under a completely delusional state, right? I mean, you're running on a shared system. Somebody might have been crashing the file system at the time. So if you're writing to a file, your code is going to look much slower than it used to be. You might have been running with the wrong affinity, so that your performance is much slower than it should have been. The key here is that you need to control all these things. You need to run with a clear affinity for your tasks, your threads, and your memory. You need to be able to repeat the experiment multiple times, so you shouldn't do everything by hand. If you need to set several paths, several environmental variables, make sure all those are in a script. And when you want to rerun your test, you just rerun that script. That way you don't forget about the 17th environmental variable that you use for that particular test, because that might be important, especially if you look at a code after a few months and you haven't been testing. It's really difficult to remember exactly how you set up your runs originally. There are things you cannot really control. You're in a shared system, and while we allow you to use the nodes in an exclusive manner with nobody else sharing your node, you still share your network, you still share your file system. So it is important that you run multiple times to give yourself an idea of whether the performance you saw in the first run is consistent, or it was just a complete outlier and the real performance is something different. So it's important that you run your code at least a few times. You don't need to run it 100, but 3, 4, up to 10 to give you an idea of whether the performance you're seeing is what you should be expecting. Many people worry about the floating point count, how many flops per I can push through the system. First of all, there's plenty of applications where the flop rate is not the limitation for the performance. Very often, it is more related to your ability to retrieve data from memory quick enough to perform those operations. Also, in modern Intel chips, it's very difficult to get an accurate count of floating point operations from the hardware. And the reason is that they count instructions issued instead of instructions retired. So an instruction may be issued several times before it's actually executed, because the processor can issue an instruction, but then it's not able to retire it because the data is not available to execute the instruction. And so the instruction will go back onto the buffer and be reissued later on until the data is available. So you can get overcounting. So while you can look at these numbers, at floating point numbers, you have to be a bit careful the way you interpret them in chips like Sandy Bridge, Ivy Bridge, and Haswell. So, and this is the only time I'm going to mention this, but I just want you to be aware of it in case at some point you see some really strange result. Remember this, because it might explain why you're seeing certain behaviors. Now, the simplest way to look at performance of your code would be just to time the execution, right? You just use user being time minus p, run your code, and it tells me to run for 10 seconds. And then you change something in the code, you run it again, and you get a different value. The problem with doing this is that you really have no idea which parts of the code are slow and which parts are fast. You just get in an overall measurement. So this is extremely simple to use, but it's not very useful for you to have any actionable information to go ahead and change your code. A step above from that in complexity is including timers in your code. And that's, for me, is actually many steps above in complexity, because if you have a complex long code, particularly a code that you inherited from somebody else, or a code that comes from a large development group, you probably don't have the time to go and introduce timers by hand inside the code everywhere to see which functions are fast and which functions are slow. So this is something you can do, and it's something that is sometimes useful in code you are developing, because you're already writing the code, why not put a few timers here and there to look at the performance. But if you're trying to optimize a much larger code, you probably don't want to use either these or the OpenMP or MPI timers because it's just too time consuming. The tools I'm going to introduce to you allow you to get this information in a much easier way. And we have about an hour and 20 minutes to go through this. So stop me at any time if there's something that it's not clear, or if there's something you want more information on. I'm going to start with the GNU profiler, gprof. Gprof gives you 3 types of profile, and what it does is it writes a text file with these 3 profiles. Well, actually, with the first 2 in general. It just requires that you recompile your code with the -g flag. The 3 profiles that you get are a flat profile, which essentially tells you this is how much time each function in your code took to execute. This is how many times this function was called. And that might be useful because if you have a function that is called 20 billion times in 20 seconds, you might want to consider whether the overhead of just calling that function is actually damaging your performance. You have the call graph, which essentially allows you to build up a representation of what the code is doing under the covers, which subroutines are functions and calling which subroutines are functions. And I'm going to give you a very detailed example of how to interpret both these 2 profiles, since gprof is a tool that you have on every system and is very simple to use. Annotated source, I don't normally use this. It essentially gives you a source code with a number besides each line that tells you how many times that line has been called. And that can be useful sometimes also for the purpose of heads might be hurting your performance, since you might see a line of code that you did not expect to be called many times has been called many times through an execution. But that's really not the most common way to look at gprof data. So typically you build with the -pg flag with GCC or the -p flag with the Intel compiler. You add the -g flag not to introduce a reduced level of optimization, but to introduce symbols. So when you see the text report, it actually writes function names that you identify instead of strange names assigned by the compiler, right? So the -g flag is there just to give you those names from the code. Something you should keep in mind for particularly the Intel compiler is that when you use the -G flag, it automatically downgrades your optimization level to 0. So if you want to compile with full optimization, which you want to for a profiling run, what you have to do is add your optimization flag after -G. So in this case, you could do ICC -G, -P, -03, for example. Otherwise, you would be profiling a code that is not built with the correct optimization level. And so the results you get from there are really not going to be very useful to you. Once you have the code built in this way, you just run it as you would normally run it. There's nothing special about the run. At the end of the run, you will have a single file called gmon.out. And you will have to use that file to generate the text profile. You use it with these commands. gprof will simply give you a flat profile and a call profile. dprof -l will give you a line-by-line profile, and dprof -a will give you the annotated profile. And what we're going to see now is an example of what this text that is generated as the output is. Because initially it can look a little bit confusing. There's several things to look at here. First of all, you have the percentage of time spent in each routine, and then you have it broken down in cumulative and self-seconds. Cumulative would mean if I call any subroutines under myself, cumulative includes the time that those routines executed into. Self-seconds is just the seconds that I took to do things without including any call. You have the number of calls, which is 1 in most cases, apart from mat-sqrt, which is 2 calls. And then you have self-seconds and total seconds for each call. Now, in this case, the things that I normally look at are the cumulative seconds and the number of calls. If I look at this carefully, in this case, I have, well, that gray block should have been shifted 1 line up. In this case, we have 3 routines, which are the mat square root, the mat cube, and the sys cube, that take literally almost 100% of your time. It's 99.4% of your execution time. So what you want to do is you want to focus on those 3 routines, right? You want to go to the source code where those routines are called, and you're going to try to figure out if there's any way you can improve them. So if you had a code with 578 routine calls and you run gprof and you can focus on 2, that's already saving you a lot of time for not very much effort. The only effort you did was to rebuild with the -pg flag. Right? This is a very useful tool. It doesn't give you very detailed information, but it gives you some level of detail. For example, if you look at the call graph profile, the first thing that you notice is that it's broken in several blocks with different index numbers. Actually, if you look at the rightmost column, you will see that each function call has an index number. That index number is used within the graph profile to identify who is calling who in the code. For example, in this first block, you see main is indented towards the left. So that means that main is calling all these subroutines. And we could represent that in this way, right? So the flow of the code is we start main, and within main, there are independent calls to each of these routines. Now, if now we go back to the call graph profile, and we select, for example, this mat square root, which has index number 2, we know that we have to go to the block with index number 2 here, and that will give us additional information about the execution. And when we look at this, we see this function is being called by these 2 guys on top, like main and sys square root. So we can go back to the graph that we originally designed, and we can add these calls. So now we have these mat square root, and we see that it's called both from main and from sys square root. And in this way, checking the indexes and the consecutive blocks in the call graph profile, you can build your own call graph profile manually. Now, this is very time-consuming for a large code, so you're probably not going to do this. There are other tools that I will show you later, but this is much easier to do. But if you want to be able to interpret the call graph profile from gprof, this is the way to do it. So a last example, if we were now to look at the index number 3, which is c square root, you can see that c square root is called from main, and it itself calls mat square root and bec square root. And if you look at the number of calls too, you will see that this is only called once, but these two functions or subroutines are called twice, but only one of those 2 times they are called from this system square root. And we can add this additional level of complexity to our call graph, and we see that bec square root is called both from main, which was something we originally had in a graph, but now we also know is called from c square root. And you could continue doing this until you have a complete image of the flow through the code. But like I said, this is not very useful for large codes. If you're just playing, you're developing a small section of code, this might be useful to you. But in general, it's not something that you want to look at. In general, you want to look at the flat profile, you want to look at the top 2 or 3 functions that use most of the percentage of execution time, and you want to focus on those. Something I haven't mentioned is there is a way, if you're running a parallel code with gprof, you can get independent gmon.out profiles for each MPI task. You have to use a gmon underscore prefix variable, and you have to assign a different name for the file for each MPI task. So you could script these fairly easily, and you could compare which functions take most of the time in each of the MPI ranks to see if there's a difference, and you see that you might have an imbalance or something that you're not expecting is happening. But in general, the good thing about gprof is that it's very simple to use, and it gives you the parts of the code where most of your time is spent. Now let me move on to PerfExpert. PerfExpert is a tool that, well, it says brand new here, but it's actually been in development for more than 2 years. So by now it's a reasonably a stable tool. It's fairly easy to use and understand, and what it will do is it will tell you, it will look at very detailed execution information, but it will not give that information to you raw. It will digest it and it will tell you, your code has a problem with accessing data, or your code has a problem with not doing enough vector operations, or your code has a problem with failing to find data on cache level 2. So it will simplify things for you. Under the covers, it uses HPC Toolkit, which is something we'll talk about in a few minutes, and it uses PAPI to collect hardware data directly from the system. It's mostly geared towards sequential code, although you can also use it to look at MPI parallel code. It will not give you any information about MPI performance. It will just give you information about overall code performance. And it can also give you optimization suggestions. So after doing the run, it might go through your source code and tell you, hey, you should probably invert the order of these 2 loops, or you should try to fuse these 2 loops. And some of those work and some of those don't work. It's a very hard job to have a completely automated system that tells you what optimizations are going to work well in your code. Profiling with PerfExpert is pretty straightforward. If you're working in Stampede, there's a couple of modules you need to load because PerfExpert depends on them, in particular PAPI and HPC Toolkit. You compile your code with -G and full optimization. Essentially, -G is to allow you to refer the performance back to a particular line in your code. And in your submission script, if you're using one of our Slurm submission scripts, you just need to use PerfExpert and then a number that denotes which functions you want to see information about. So if it's 0.1 is any function where the code spends more than 10% of the execution time. And then you just give it your executable and any arguments that you have. And what this will actually do is it will run your code several times. I don't remember now if it's 5 or 7, but it will do multiple runs. In each of them, it will collect a different type of information from the system. So it will read different hardware counters. It will analyze those, and then it will output some conclusions about your performance and some suggestions on how to improve your code. So an example output, I don't know how well you can see this from there, but I hope it's not too small. An example output would be this. It would essentially say, hey, your function collision, which is called from line 68 in this file, you're spending almost 40% of your execution time. It will tell you the ratio of floating point to total instructions. In this case, it's 100%. There's no integrated data access, blah, 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 blah. And then it comes down to performance assessment. And maybe I can stay on that slide for a minute. So overall, the execution is very bad because your cycles per instruction are 4.51. Now, the way it does this is still based on floating point. So you cannot trust that part so much. The fact that it says it's 4.5 might not be accurate. What is accurate is the rest of the information here. For example, it's telling you that you're spending most of your time in data accesses, which for this code is absolutely true. It's telling you that you have a fair number of L1 data hits, which is good because that means you're reusing some of the data in L1. You're not just throwing it away all the time. You're reusing some of the data in L2, but not a lot. But you're never reusing anything in L3. So essentially, you have a lot of last level cache, which in this case is L3 misses. It gives you additional information about instruction accesses and so on. This is typically not a limiting factor for most codes, but it can be. And in this case, it shows that most of the floating point instructions are actually fast floating point instructions, meaning that they have been optimized nicely by the compiler. So overall, the main problem, if I were to look at this, my main concern with this code would be data access. I would say, hey, data access is really bad. In this case, the evaluation is spot on. This is a code that is memory bandwidth limited. So I would expect that data access is a problem. You will see that the scale here doesn't have any numbers. It's just good, okay, fair, poor, and bad. And that's based on this group of developers has a lot of experience running codes in our system, and they have a fairly good idea of what represents a bad execution profile and what represents a good execution profile. So they're interpolating that with the specific data they collected for your run and just trying to give you an idea of how well your code is doing. The advantage of PerfExpert is that you don't have to be an expert on what the numbers they're collecting mean. You can just trust their evaluation, right? And at the end, it will give you some suggestions. In this case, it's telling us that, hey, instead of having independent loops and saving something to a temporary variable, then loading it again from memory, just try to fuse the loop so that you don't have to reload from memory and you reduce the number of memory accesses, which seems a fair suggestion. As you can see, it gives a fairly decent explanation of why it's providing this suggestion as a way to improve the code. Now, PerfExpert has a much more advanced way to use it, where it will do code-to-code translation. It will generate a series of suggestions for improvement of your code. It will implement them in the code. It will generate a new binary. It will run it. It will evaluate it. And it will do this multiple times. To do that, you have to invoke it with the -m or -s options. And you need to have the source code and a make file available in the same directory that you invoke it, or tell it where to find it. If you do that, you should probably have a nice backup copy of your source code just in case. And they tell you this when you start PerfExpert. So they're very cognizant that, you know, even though they've tried this a million times, it might go wrong the 1,000,001. If you want to get the code and documentation, these are the two best places to go. And the main developer, Leo Fiaggio, is located here at TAG. He's a very responsive person. So if you want to try PerfExpert and you have any issues, you can contact him or me, and we can help you with this. So PerfExpert gives you a little bit more information than gprof, but you still don't need to understand the meaning of all these hardware counters and anything like that. So it's a nice middle level information tool. Now, so far, I haven't talked at all about MPI. And when you're running on a machine like Stampede, you're very likely to run an MPI code. There's many tools to profile MPI code. There's MPIP, there's IPM, there's some of the MPI libraries come with their own ways to do performance monitoring. The one I'm going to talk about today is IPM because it is fairly simple to use and it can give you a ton of information. And you can control reasonably well how much information you get out of IPM. So if you think that the full report that it gives you is way too much for you, then you can also read essentially a 10-line text report that tells you, go here and figure out why this is taking so much time. Yeah, so IPM is essentially a portable profiling infrastructure, but focused on MPI. Like I said, the level of reports can vary a lot. This is still, in a way, it's smaller than Tau, Puppy, or HPC Toolkit, but only because it doesn't give you access to hardware counters. It's just focusing on MPI. So on the other hand, Tau will never give you as much MPI information as IPM is able to give you. It's a very useful tool to look at things like scalability or load imbalance. You have a code that you've been running on a few MPI tasks, and suddenly you start scaling up and you see your performance drops or levels off and you're not able to determine what the problem is. You probably want to do a couple of tests with IPM at different scales so that you can say, okay, once I go over, say, 128 cores, then I'm starting to see problems. What is the difference between that run and the run at 256? You can look at those two profiles and get some idea of what's going on. The other nice thing is that you don't have to modify your code at all to run IPM. The only thing you have to do is remember to build with the -G flag. To run IPM, you just do a module load IPM, and then what you have to do is you have to export an LD preload variable, and that's to make sure that IPM can intercept and use its own MPI calls, which actually wrap the regular MPI calls and capture additional information. You need to export IPM report to tell it what kind of report you want, and that can be terse, full, or what's the third one? Or none. Yeah, well, none doesn't seem very useful, but I guess if you have a system where they do an LD preload of leave IPM.so, that might be a way for you to avoid collecting any information. And then the way you run is just the same way you always run an MPI job here at TAG. You do an IB run, you're executable. If you use this in a different system that is not TAG, then use your MPI launcher. It might be MPI run_RSH. Everything else should work exactly in the same way, as long as the libraries are in your LD preload and everything else is correctly installed. So the workflow would be to export your LD preload. You tell the system what kind of report you're expecting. You set up a threshold, and this is an optional step. By default, it will do, I don't recall, I think it's 0.1. But you set up a threshold that says, okay, only look at MPI calls on MPI sections that take more than 30% of the total MPI communication time. So I typically don't set this because I want to see as much as possible, but it's something that allows you a fine degree of control on what's going to be included in the report. And you will run your code as normal. This will generate a directory with all the information in an XML format, which is completely unreadable by any human being. But you can use IPM_parse with the -HTML option, and you give it that directory name. And it will generate a new directory that has HTML files in it. And so you can open them with any browser. You can actually do an SCP from Stampede to your laptop and then look at them at leisure at home or whenever you have time. So the nice thing about that is that the analysis part you can do anywhere in your laptop. You don't have to do it in the system. So this is an example of typical output from IPM. Let me see. So what you're going to see is what command was used. In this case, I was using a really badly implemented parallel matrix multiply that sometimes I use for profiling examples. I was running on 16 MPI tasks on a single node. It took less than a second to run because this was a trivial example. I will tell you the start and stop times. And you might not normally look at this, but for example, if you're reporting a problem to us, this might help us look at the logs to see what was happening between those 2 hours, see if there was some issue with the network that might have affected your execution rate. So sometimes it's useful. It will tell you how much memory you were using total, in this case, about 5 gigs. It will not report gigaflops per second because we have not set this up to use PAPI to read floating point operations. And it will tell you what percentage of your time was spent in communication, which is the most useful part, right? So what you can expect is that you run, say, 16 tasks, then 32, then 128, then 2,000. You should normally expect that if you're using the same workload, the percentage of time spent in communication is going to keep increasing, and your scalability is going to get worse, right? But a good way to get a number, to put a number on how good your scalability is to look at this percentage of communication. And this top part that ends here is essentially what you would get if you ask for a TERS report. So the TERS report will just tell you, okay, you're doing 25% of time in your communication, that's it. The full report will include the second section, where it would essentially give you some statistics on all this information that it gathers. So, you know, the average time spent in communication is 20%, but you had some tasks that spend as little as 16, and some tasks that spend as much as 78, which probably means if I see that, I immediately think there's a master-slave configuration here somewhere, because there's one guy that is coordinating all communication. That's why he spends 80% of the time in the communication range, right? That's the only thing that would make sense to me. But the interesting part is that you can come down here to this bottom section, and now you see what percentage of time, of wall time, and what percentage of the MPI time each of these functions that appear in the code took. It will not tell you on which line in the source code they appear, but it's a good start to see, okay, I'm doing a lot of broadcasts. They're actually taking 60% of my execution time. So go to your code and figure out why you're broadcasting so much data, because there might be a better way to do that. You might be able to just do point-to-point communication of smaller chunks of data and overlap those exchanges or something similar, right? So you didn't have to do a lot of effort. All you had to do was to export an LD preload variable and build your code with -G, which, by the way, if you don't know this, when you build with -G, as long as you still specify your optimization, you don't lose any execution time. Your code is still going to be optimized. So you have no loss of performance by compiling with -G, and it can come in really handy later on. So it's probably something you can do always. It's not going to hurt you. And you get a fair amount of information about your MPI performance. Now, if you do that IPM parse -HTML step, now you can get a new directory that will have an index.html file and has a ton of additional information. And this is a fair example that a colleague of mine ran, probably in Ranger. Let me see. Yeah, I'm pretty sure this is a Ranger run. But this has not changed. This looks exactly the same today. It will give you some information about PAPI events. PAPI events are events that are read from hardware counters and relate to things like floating point operations, level 2 cache access, etc. And then it will show you a pie chart with who used most of the MPI time, right? So in his case, he clearly has a lot of MPI all reviews that is taking more than a third of his total time. And after that, he has some broadcasts, some wait any, so he clearly has some asynchronous communication. And don't be surprised if you see a lot of time reported in MPI wait or MPI wait all. All that means is that when you do an I send or an I receive, so an immediate send, an immediate receive, there's barely any time spent there. All the time is spent on the barrier that is represented by a wait or a wait any. So when you see a lot of time spent on a wait any, don't think, oh, what's wrong with that wait any? No, you need to look at what's wrong with the communication that wait any is completing, right? Besides this, it will give you a breakdown of every single call type in the code. So every call that was repeated multiple times will appear here with the buffer size that it was used for that call, the number of times that it was called, the amount of time that you spend on that call, both the minimum and the maximum. So this can be extremely useful. For example, if you see that you're spending, and this is not the case in this example, but if you see, well, yeah, there's a case here. So you see these MPI I sends, they're using almost 5%, 4% of the communication time each. They're tiny. They're only 8 and 4 elements long, right? So when you're on that range, your effective MPI bandwidth is extremely low because you're limited by latency. So when you see something like this on a report from IPN, you need to think, okay, is there any way I can gather more data and send a single message that is longer? Because that's going to be more efficient. So you can see there's a ton of information in the HTML report. Not only that, but it gives you a whole bunch of plots representing things like what's your workload balance, not directly as workload balance, but for example, as memory balance or floating point operation balance. So through your MPI tasks, who was using most amount of memory? And for most people, that's going to be a flat profile. And if you see it, and if you expect a flat profile and it isn't, you know there's a problem. It will show you a communication balance, and that's not only ordered by task, but it also shows you in different colors the different calls, and so you can get an idea of this first block of processors spends a lot more time waiting for that MPI all reduced to complete than anybody else. So, you know, you should probably look at what's happening there, why that's taking place. This is information you can never get out of gprof or PerfExpert or anything like that. Something that is useful to look at, and don't worry too much about all the crazy shapes, is to look at how much time you spend on communications depending on the message size. Because, like I mentioned before, when we give you the bandwidth of the system, we talk about the bandwidth for very large messages. When you have tiny messages, the effective bandwidth is really, really small. And so when you look at this plot, if you see that most of your messages are down here, you should try to find a way to move the map towards the right where the buffer size is a bit bigger. And in some cases you can't, and that's fine, but this is a good tool to look at that instead of having to go through your code and record for every message which message size you're sending and so on, because that's very, very time consuming. This is number of calls per buffer size. I think that the percentage of communication time is much more useful to you because that's what you care about. You don't really care how many times you call a function typically. You care about how much time was spent in calling that function. And it will also show you a quick little plot of communication topology that will show gray or black plot or dots when two tasks communicate with each other. And this will give you an idea of, okay, is this mostly a point-to-point code, or is it an all-to-all code? And you know, if you had typically you want to see a sparse matrix because that means that you have a few point-to-point communications, maybe some broadcasts, but that's it. But anyway, this is a good tool to get an idea of, particularly in a code that you have not written, who is talking to who during the execution. So that's pretty much all the information you can get from IPM, and you can see that it's a lot. I mean, you can really get a lot of information by just exporting 2 environmental variables and running. I find it really useful to find things like workload imbalance, find it very useful to find things like I'm doing a scalability test and I just want to look at the percentage spent in MPI. It's not very useful when you already know what your performance issues are, because then you don't need to use an profiling tool. But also, if you need information on which exact lines in the code a call happened, and this is not moderately useful, because you're still going to have to do some digging to find that out. It's also not useful to give you information about overall performance. This is focused on MPI only. If your concern is that when you run on a single task on a single thread, the code doesn't work very fast, this is not going to help. So for that, we have all the tools. But this is a tool that is excellent to look at just the MPI performance and possible issues with your MPI communication strategies. If all you want to see very quickly is that brief text report, and you use an Intel MPI in a Stampede, you don't even have to use IPM. All you have to do is export these 2 environmental variables. You export IMPI stats equals IPM, and you can do IPM column full, but it's going to give you the same thing. And you export IMPI stats file, some file where you want to store that data. And the next time that you run your code, you will write down this text report, as if you had run with IPM. So it's a very simple way to get a performance report every time you run without the need to do anything. So if you build your code with Intel MPI, you can simply export those 2 variables in your submission script, and every time you will get your MPI performance information. You can get a lot more information than this. You can actually get information about every single MPI call made in your code, with the buffer size, with the line, with the origin and destination ranks. But to configure it to do those things is a little bit more complicated. So I will refer you to the MPI reference manual from Intel. It has a section, if you look for IMPI stats in the PDF document, it has a whole section, 4 or 5 pages, explaining you how to set up different data collection strategies. I find that for most users, the only thing they're really concerned with is scalability. So to begin with, they just need to know what percentage of time goes into their communication. And for that, these 2 lines are really all you need. But if you want to dig deeper, the Intel MPI stack can definitely give you a lot more information. Any questions so far? So far we've covered 2 fairly simple ways to look at serial code performance and a fairly simple way of looking at MPI performance overall. And those are basic tools, and if you use them, you're probably about 4 steps ahead everybody else in the system, because there's very few people that actually bother looking at their performance. But if you're going to go beyond that and you want to look in a lot of detail at your execution, particularly if you have a little bit of knowledge of the structure of the processor, you understand what a level 2 cache, what a level 3 cache is, then there are tools that can give you a lot more information on your execution performance. Typically, the problem these have is that they're not easy to install. They have tons of requirements. But the good thing is that you don't have to take care of that, because we do that for you. So all you have to worry about is learning how to use them and learning what the reports that they produce mean, which is typically the hardest part to interpret. Collecting the data is not very difficult, but understanding what the data is telling you is a completely different story. Most of these, like IPM, gprof, and PAPI, which I'm going to describe in a minute, to collect information about both the MPI performance and the throughput of a serial code. Very quickly, I will mention PAPI several times. PAPI is essentially a programming interface to access data from hardware counters. And most of the tools that I'm going to describe now use PAPI under the covers to periodically sample the system for events that are recorded in these hardware counters. You are very unlikely to use PAPI directly from their source code, more than anything because it's a time-consuming thing. The first tool I'm going to talk about is HPC Toolkit. HPC Toolkit I like because you don't have to do a lot of effort. You also rebuild your code with -G. That's all you have to do. It uses a binary instrumenter so that it captures things on the fly while they're executing, which means you don't have to modify your code or you don't have to rebuild your code in a strange way. It uses sample-based measurements through PAPI, so every now and then, every few milliseconds, or whenever you actually want, you can configure that. It will ping the system to get to read hardware counters, and it has very good scalability for large execution. It also has pretty good analysis tools, and you can install them locally on your machine, so you can just get the data files and look at them in a coffee shop or whatever. You don't have to do it in Stampede, which sometimes can be inconvenient if you're remotely located and your X11 performance is slow, like you mentioned before. So this is a good thing that HPC Toolkit has. The way it works, essentially, you have your source code, you're going to compile it, and you're going to get your optimized binary, nothing different from the way that you normally compile. You're going to run HPC struct on your binary. That's just going to generate a file with information about the static structure of your code, what kind of loops you have, and a few other things. And then you're going to run prefixing your binary with the HPC run word, which is going to generate a color stack profile. Then you're going to have another step, and I'm going to go through this one by one in a minute, where you correlate the information you just collected from the system with the static profile, and that will generate the database that you can look at with HPC Viewer. And this looks like tons of steps, but actually what it means is just this. You build your code with optimization and -G. Instead of running my executable, I ran HPC run space my executable. And this has worked every time I've tried it. This has worked, so it's never failed for me, unlike Tau or some of the Scalaska runs that I will talk about later. You can also do a parallel collection with IV run, HPC run my executable. Independently of this, at any time, you have to run the HPC struct binary to get the structure of the code. And that will generate a file called myexecutable.hpc struct. So it's pretty obvious what the output is. To interpret the profile, you're going to run that line HPC prof -S for a structure. You give it the structure file name, and then you give it the measurement file. And typically, the measurement directory is called HPC Toolkit application name measurements job ID. So it's a pretty long name, but it's easy to identify. And also, if you run multiple instances in the same directory, you get multiple job IDs, so they don't stamp on each other. To view the results, you're going to launch HPC Viewer. With this command, HPC prof is going to generate a new directory called HPC Toolkit, my application database, blah, blah, blah. And an HPC Viewer is going to allow you to look at a fairly detailed level of information about your code execution, and it's going to allow you to look at the source code and the exact lines in your source code that you need to focus on. And I'm going to show you a few screenshots in a minute so you can see how to go through that process. While you can do this, the only thing this is going to collect, as described in this slide, is runtimes. So it's not going to collect hardware counters. If you run it in this way, the only thing it's going to collect is essentially the same information that you got from gprof, but with a nicer interface. Now, it's very easy to configure the events that you want to collect if you know what they are. And that's a completely different issue, because sometimes we don't know what they are. It's kind of hard to know which ones are programmed correctly and which ones are not. But the general structure is that you will call HPC run -C and then the name of the event, and optionally a period that you want to measure it over, and then your executable. So an example would be HPC run, and then I'm going to ask for total cache misses that affect level 2 of the cache. So how many times during my execution did I look for something in cache level 2 and it wasn't there? I'm going to look at data cache accesses. So how many times did I try to access L2? The reason I want to look at these two is that then I can divide them and I can get number of misses over number of accesses, and that will give me an idea of how badly my code is trying to reuse L2 data, right? If my number of misses is very close to the number of accesses, that means I'm never reusing L2 data, and so my code is going to suffer for that. And I'm also requesting PAPI total cycles, which is the total number of cycles that the code ran for. Right? And that's just to give me an idea of also which functions in my code take the most cycles. So who is literally taking most of the time in my execution. This is a special event called wall clock. And if you use that one, you cannot use anything else. So you cannot combine that one with any other event. Now you might be wondering, how do I know these names? PAPI, L2, TCM, you know, where did that come from, right? To look at those, you just do an HPC run -- list events, and you will get probably about a page, maybe a page and a half of event names with a brief description. You would also have two columns that says, is this profilable or not? And so if it says it's not profilable, that's a defined event, but in the particular processor that you're working with, you cannot collect any information about it. And that's just because the vendors program these things in different ways. Some of these counters are missing in some processors, and so on and so forth. But this will give you the information on what you can collect overall, and with that you can build your HPC run command line. No multiplexing. So somebody might be wondering, what is this multiplexing business? Most processors allow you to collect a certain number of hardware counters simultaneously without multiplexing, which means without having to serialize the access to the hardware counters. In the case of Sandy Bridge, it's a fairly large number. It's probably 7 or 8. You can collect a lot of stuff. But in other chips, it might be 2, or it might be 3. So if you specify 4, then you're not going to be collecting at the frequency that you specified. You're going to be collecting whenever possible. So every now and then, you're going to have a slightly less quality of measurements because there's multiplexing. Generally, multiplexing works quite well, but HPC Toolkit does not support it. So if you want to collect lots and lots of events on a single run, just make sure that you know what's the maximum number of events you can collect in Sandy Bridge, which I'm pretty sure is 7, but you would want to check that because otherwise you would get execution errors with HPC Toolkit. Now, when you open the HPC viewer, this is the view that you normally get. It's a pretty simple, pretty clean interface. At the bottom here, we'll show you the events that you requested, both in inclusive and exclusive counts. The same concept as with gprof and time. Exclusive is just my time, inclusive is my time and anybody that depends on me, that was called by me. You will see the source code on the top, and you have a small window, a small toolbar that shows you some useful things. You have a hot path, you have a derived metric, and then you can change the columns that you view. So if you ask for 7 counters, you would have 14 columns for inclusive and exclusive. So that's way too much. You normally want to eliminate a few of those and just look, for example, of exclusive time. You can export your data in CSV format, which if you want to do additional processing might be useful. And you can change the font size, which I don't think you probably care about. But probably the most useful thing here is the hot path button. When you hit this, it will highlight on the bottom window what is the most expensive execution path in your code. So by looking at this directly, you can see which line in your code, and in this case is this matmult.c line 120. You can see exactly which part of your code is using most of the cycle. So this is really useful. You don't have to worry about the structure of the code. You don't have to worry about anything. You just go hot path, tell me where I'm spending most of my time, and immediately I go and work on that. Since you can also compare your cycles or your time, whatever you measured here, with other hardware counters like total cache misses, total cache accesses, that can give you an idea of, okay, this is really expensive. Maybe the reason is because it's trying to access L2 continuously and always failing, so I need to work on my data accesses, for example. Something that is also very useful is the fact that you can generate derived metrics. For example, we collected total cache misses and data cache accesses. What we probably want to do is to generate a derived metric that is one of those divided by the other. And that way, you just look at that. And if it's 0.9, we know we have a problem because we're missing all the time. If it's 0.1, we probably don't care about that. And we know that the performance issues come from a different place and not from L2 accesses. Once you generate, and you can do fairly complex stuff with this derived metric. It's not just plus and minus. You can do fairly complex operations. Once you create it, it will just appear as a new column on the bottom. And you can select it, you can save it with the rest of the information. It's pretty, the nice thing about HPC Toolkit is that it's very easy to use. It can collect a lot of information in terms of hardware counters, and it still has a fairly easy to use interface where it tells me immediately, this is your most problematic code area, and it shows me the source code and the line. So I can very quickly look at that part of the code and focus on the problem. Something that you might want to do sometimes is to actually trace the code in case you think you have either a workload imbalance and somebody is spending too much time doing something and everybody is waiting for that guy to finish. This is extremely simple to do with HPC Toolkit. The only thing you have to do different from the previous execution is you add the -t or -- trace option to HPC Run, and that will collect detailed timing information. You go through the same procedure. You run HPC extract on your binary. You run HPC prof using that structure. And then instead of using HPC viewer, you use HPC trace viewer. With this. And what that gives you is an interface of this type. Each of those horizontal lines represents a timeline for each of the MPI tasks that you executed. And each of the colors represents different function calls. So in this case, we see everybody's executing pretty much the same thing to begin with. And this is probably a broadcast. You can see it here on the right side window. On the bottom here, you can see the different depths. So as you go down here, it's a different number of calls from different functions. At the place that we're at, what you're going to see is essentially main is executing a broadcast, but then broadcast internally within the Mbapich2 library is calling all these other functions to complete the broadcast. You typically don't care about that part, but you might care if the function is not a broadcast, but is one of your subroutines that calls another subroutine, right? This will allow you to zoom in and look at all of those in detail. The good thing about this interface is that it's very simple. If you run 32,000 tasks, this will still be very responsive because what they do is they essentially interpolate so that they don't have that much data to handle, and they will only display the full amount of data when you zoom in on a particular region of the timeline. So this is a tool that works extremely well at large scale. Something that is useful when you have lots of tasks is the ability to focus on one or two of them, say task number 0 and task 27, just to see if you see significant differences between the timelines. You can do that by filtering ranks. So there's an option here in the view menu where you can apply a filter. And the filter that you can apply is just add rank number 0, add rank 27, and then your display will remove all other ranks and just show you those two. So it's a very simple to use tool, but at the same time, you can collect any hardware counter information that is available in the system. So it's very useful. Now we have an Intel, now in this category of HPC toolkit, things that can collect hardware counter information, there's many other things. There is VTune from Intel, there is Tau from, I think it's Oregon State, I don't remember. There is Escalaska, which is from Jülich in Germany. All these guys are more complicated to use than the other tools I've described, and I think of all of these, HPC toolkit is the simplest. Now, VTune is not particularly hard to use either. We have it available in Stampede, and the advantage it has over HPC toolkit is that if you're using the mics, you can also do profiling on the mic through VTune. You simply load the VTune module, and again, you need to compile your code with -G. That's just to get source code line information. And there's two commands that you will need to use probably, amplexc.cl, and the reason it's called amplexc is because they call it VTune Amplifier XE, which is a terrible name, but that's what they want to use. And then if you want to use the GUI, then you're going to use amplexc GUI. And it has the same behavior in the host and the Xeon Phi coprocessor. The only difference is the type of analysis that's going to be available to you in either of those. So to collect, for example, very quickly, what are the hotspots in your code? And this is essentially just going to run timings through your code. You just do amplexc -collect hotspots executable, and that will take care of the collection. If you're wondering what things can I collect apart from hotspots, amplexc.cl -collect help will give you a full list of everything that is available in the system, everything that you can call. Typically, you probably want to do a first run for hotspots, and after that, you want to do a run that is more specific, looking at either concurrency or port saturation or something else. But typically, the hotspots run is the first one you want to do because you want to know which part of your code is taking the longest. And the advantage that VTune has over some of the other tools is that it will not only show you the source code line where things are being expensive, but you can go and look at the assembly associated with that source code line. Whether you want to do that or not, that's a different issue. But sometimes you find problems that you cannot explain by looking at the code. Then you can go look at the assembly, and you can see that the way the compiler generated the assembly is going to create problems for you. And so you might be able to change things around. So it gives you even more information than HPC toolkit, but the complexity of the analysis also increases. Now, these are some of the analysis types that are available on Stampede, and I don't really want to spend any time here. This is just more for your reference than anything else. But all of these are fairly self-explanatory. Hotspots is going to tell you what's the expensive part of your code. Bandwidth is going to tell you how much memory bandwidth was used through execution. Which one can be strange? I guess SMB port saturation can sound weird. That port saturation refers to the chip has different ports that do different things. Some ports issue floating point executions, some points generate memory addresses, some ports generate integer arithmetic operations. So when you look at port saturation, you can see, okay, I'm saturating address generation. That means you're accessing memory so often that the chip cannot access memory, not because of a lack of bandwidth, but just because the chip is unable to generate the addresses in memory to gather the data. Now, that's a fairly uncommon problem, but it's something that you can look at. So VTune gives you a lot of depth into the information you can collect about your performance. Once you have your collected data and you want to look at it, you could generate a brief text report with the command line interface. That will be that report summary. And then you would use -R and the results directory. Or you can start the graphical user interface to look at things in more detail. If you want to use the graphical user interface, you're going to have to use a VNC session because that is extremely slow over SSH. Even from my house, that's extremely slow. The screenshots I did here 2 days ago because from my house it was so slow I just couldn't wait for it. So if you want to use the graphical user interface remotely, go to the Stampede user guide or ask one of us how to establish a VNC session. That's going to be the best way to go for BTune. The summary report that you see in text is very, very brief. It doesn't really give you a lot of useful information. It's going to look something like this. It's going to tell you some details about the kernel you used to run, the processor, the frequency at which the processor ran during the execution, number of CPU counts, and then elapsed time, CPU time, and average CPU usage. So this is really not very useful. The part of BTune that is very powerful is the graphical user interface. Once I load, for example, a hotspots results file, it will give me a fair amount of information about what parts of the code seem to be most expensive. In this case, you can see that I have an MPI receive. When you see P before an MPI, that's an internal MPI call, but that typically corresponds to your MPI underscore receive. It would also tell me out of the 16 processors in this chip, which ones were busy while I was doing this, and you will see that in this case, essentially one. The reason for this is that this was a parallel run, and BTune doesn't know anything about MPI. So what I did is I loaded the very first results file, which is for task 0. So of course there was only one processor busy because I only loaded the profiling results for one processor. If this was threaded code, it would actually show you how busy each process was on that graph at the bottom. Now, if you go here you can select different ways to look at your profiling information. You can do a bottom-up, a color collie, or a top-down tree. For me, the thing that makes most sense most of the time is the top-down approach, because I want to know, okay, main called this guy called this other guy, and this is the expensive part. If I do a bottom-up, then the same thing that happens with DDT happens, which is I end up somewhere deep in the bowels of some MKL routine that I know nothing about, and I need to start searching upwards. And for me, that's more complicated. Here you will see that on the left, you have the list of functions. And you see the top-down approach here says, okay, I'm in main. The things that are more expensive were these MPI send and this initialize routine. And then it will give me some information about performance here. And you see that everything is poor, which is fine because we brought this example to be poor so that it will show up in these tools. Now, if I right-click on, say, this initialize function, it will give me a context menu where I can go do several things, including export to CSV. But what I really want to do is look at the source, because I want to know which part of this initialize routine is really most expensive. Something else you see in this window is this bottom section, where you will see essentially CPU usage. The reason this might be useful for you is if you see lots of brown and suddenly no brown, brown typically means CPU is being used. That means either you're doing I/O and nobody else and nothing else is happening in the system, or you have a section of your code where they're blocking MPI calls where nobody can do anything until the functions are finished, or something of that sort. And you want to try to avoid that always. So let's say that I right-click on initialize and I go to the view source window. What I'm going to do there is I'm going to land in this new interface where my source code is on the left. The line that VTune estimates spends most of the time in this function is highlighted. It's highlighted in light gray, so you better have really good eyesight. But it's this line 144. And if I select assembly here on the top, it will show me the assembly code that is generated for that line. And you shouldn't be surprised if for a single line of code you generate 250 lines of assembly. That's different optimizations. And the one that it applies during runtime will depend on things like, are the arrays in this loop memory aligned? Are they not memory aligned? Do they have an even number of elements? Do they have an odd number of elements? And so on and so forth. Now, looking at the assembly can be useful for a number of reasons. And I don't want to talk about assembly because that takes too long, but essentially one thing that can happen is that you look at your code and it looks like it's nicely vectorized. So your report, your vectorization report says, hey, all these loops are vectorizing, everything is great. And then you execute the code and it doesn't really perform very well. So one thing that can be happening is that the compiler is trying too hard to issue vector operations. So it's doing lots of gathering scalars and put them in a vector register and then throw them out there to be executed as vectors. And all the overhead of the preparation is actually slowing down your code. And your code might actually run faster with a minus no vec on the compiler line. So that's not super common, but it does happen. And you can see it because you will see in the assembly that the instructions for the vectorization have a mask that indicates that they're working on the scalars. But that might be too much information. So it's just, this is just a good way to get to that assembly without having to look for it by hand. And so now we've seen tools that cover pretty much everything. We have fairly simple tools to look at serial behavior, even threaded behavior. We have tools to look in detail at MPI performance. We have tools like HPC Toolkit that are pretty good at doing a good job for both because they allow you to trace and compare different tasks, but they also give you a good information about hardware counters for the overall execution of the run. We have things like VTune that allow you to drill down to the assembly generated for your code. So we have a very good overall set of tools to work with profiling. And now there's Tau. Tau is a little bit of a beast. The reason I say this is that this is a very long-term project. It allows you to look at almost everything. The only problem it has is the way it sets things up. So to do all this stuff that it does, which is essentially everything we've talked about before, all the parallel profiling, tracing, everything else, you have to tell the system what kind of code do you have. You need to tell it, okay, it's MPI, it's OpenMP, I want to use PAPI as the instrumenter, I want to call path, or I don't want to call path, or I want to face report, or I don't want a face report. So the setup is more complicated. The way you tell the system what you want to profile is through a tau_makefile environmental variable. And we have something set up by default that works for most people. But if you want to see what's available, then you have to first load the tau module. Then you will have in your environment a variable called tau. And if you ls tau, you can see all the makefiles that are available for you. These are not real makefiles. They're called makefiles, but there's just a bunch of settings that tau uses to rebuild your code with the right instrumentation. Because with tau, you do have to rebuild your code. It's not just a matter of building with -g. With tau, you have to use to substitute the compilers, ICC or GCC, for scripts called tau_cc.h, tau_f90.h, and those will rebuild your code, but including all the necessary instrumentation for the run. Now, these are fairly complex scripts, and more often than not, for large complex code, they will fail to build, and you will have to go in there and fix things manually. And this is why I always leave this for last, because this is really the most complicated tool we have. It's very flexible, but to be able to build a binary that is properly instrumented can take some time. If you're lucky, everything works, but that is generally not my experience. Once you have your tau makefile set, you need to rebuild your code using these tau CC and tau F90 instead of the regular CC and F90 compilers. And before you run, you need to export a tau metrics environmental variable, which is the way that tau sets what hardware counters you want to look at. In the same way that with HPC Toolkit, we did HPC run -E, and then we specify different events to collect. Tau does it through an environmental variable. And there's a few other options that you can pass through it, through the tau options environmental variable. But the main thing is to set up the makefile, rebuild your code with those scripts, export the right tau metrics, and then execute the code. It also allows you to generate traces of the code, which we don't enable by default. By default, we export tau trace equals 0, because if you have very long executions and fairly large code, the traces can be fairly large. So in general, for most people, we leave that disabled, but you can revert that behavior by exporting tau trace equals 1. And after that, you will run your code normally, and you will view the results with a tool called Paraprof, which is a graphical user interface. And I'm going to go very quickly through how tau looks like in the graphical user interface. When you open a set of experiments, the first thing you're going to see is what Paraprof calls the manager window. The manager window breaks down things into applications, experiments, and trials. So the application would be whatever binary you use. Experiment would be this particular run that you just did. And then the trials are each of the measurements that you've performed, that you requested. On the right-hand side of the window, you have a lot of system information that is automatically collected on the run that might be useful to debug issues. For example, it will record which system you were running on. So if you have any problems that you cannot assign to expected expected program behavior, you can always go to the logs on that machine and see if there was any issues. It also records the tau makefile that you were using. You normally don't have to look at that side. For each of the metrics that you requested, it will open a window like this one. And in this window, what you have is every single MPI task that executed. And here they're just named node 0 through 15. So those are the 16 cores that I had on a single node in Stampede. Each of the colors represents a different function in your execution. In this case, this was a very short run, so there's a lot of time spent in MPI init, apparently. And then the red color is going to correspond to multiply matrices function call. Now, if you look at this window, you already see that there's something odd here. This particular task number 0, it looks very different from all the others. It essentially spends no time whatsoever multiplying matrices, which, if I were to look at this, I would think, well, that probably means that guy is just sending work to every other processor in the system and just synchronizing the execution, not really performing any actual bars to get more information about each function. And you will see something like this figure on the left. In particular, well, the example I've chosen here is I did not click on the red, I clicked on MPI receive, which is this purplish bar that you see. It takes a long time to execute in task number 0, but doesn't really show up as a significant part of the execution time anywhere else. So if I clicked on that guy, it will take me to its own measurement window. And here you see that node 0 takes a very, very long time to do the MPI receives, but none of the other processors really spends any significant amount of time in it. So it's just a way to keep drilling into the execution to see who is to blame for the performance issues. And I'm doing this with, I started with the Linux timers metric, and you can see it in the window on the top left. So this is essentially looking at the time of execution. But I could do this with a window that has the level 2 cache misses. And the same thing will happen. It will tell me which functions had more L2 cache misses, which function had less. And then I could focus on the ones that had more misses and see if that gives me some idea of what's going on in the execution. Tau has a fairly nice 3D visualization tool where you can look at, you will see the ranks here on the right, and you will see the function calls here on the left. And these columns, each color will correspond to a different function, right? So you identify them either by the name in the axis or by the color here. And when looking at something like this, you immediately see something that pops up there. It's like, what is this green cube that nobody else does, right? There's only one task that is executing this function. So you probably want to go and figure out what that is. In this case, that green cube is actually an MPI receive, so it just matches with what we see in the 2D representation. But it's a fairly nice way to look at things very quickly. Now, if you remember at the beginning when I was talking about the call graph in gprof, it was a bit of a pain to build it because you had to go essentially relating all the indexes throughout the file. You can do this automatically in Tau, although you have to set a different makefile that includes the call path keyword. And the reason I want to put this screenshot here is because you access the call graph information through the thread menu, which I don't know why on earth anybody would think that's a good idea. If I'm looking for a call path, why do I have to go through the thread menu? I have no idea. But that's what you have to do. So in case you're wondering where this call graph option is, you have to go through the thread menu. And once you do that, you will get a small box where you can choose which threads, in this case, MPI tasks, actually. And you select one of them, and the call path for that function will pop up. And the function where they're spending most of the time will look as a bigger box, and it will look red in terms of, because that just indicates more time spent on it. And you can do this for every one of the tasks involved. And this is generated automatically. You didn't have to go through the painful process of going through all the indexing, figuring out who is calling who. In this case, this is an extremely simple example. There is only one level of function calls, right? Main just calls a bunch of functions. None of them actually call anybody else. So it's a completely flat profile. The important thing to remember is that before you even built your code, you had to set your Tau makefile appropriately for this. So if you forgot to do this, when you go to the thread menu, the call path option is going to be grayed out. You won't be able to see anything. And that's one of the things I find very annoying about Tau. If I want to do a specific measurement, I need to rebuild my whole code with their own scripts that sometimes break my build. And so it turns into an exercise in frustration sometimes to get all the information out of Tau. On the other hand, it's very powerful, and you can very quickly compare every single MPI task to every other MPI task. So if that's useful to you, it's a tool to consider. As in HPC Toolkit, you can also generate derived metrics. And as I mentioned before, this is useful because typically absolute values for a metric don't really tell you anything. I don't know what 25 billion accesses for L2 mean. Did I hit 24 billion and a half times, or did I hit none? I don't know. So looking at ratios is typically more useful. In Tau, there's an options menu where you can show the right metric panel. And once you go there, you can select each one of these quantities that you measured, and they will appear here. Then you can apply an expression. When you're done, you hit apply, and your new metric will appear as a new trial here. And you can select it and go through the same process that we did with all the other windows. And just to finish, after talking about all these tools that they'll pretty much do the same in slightly different ways. I just want to leave a couple of things with you. When you're profiling, when you're looking at performance, test every change you make. Never assume that because you fix that problem, that really fixes the performance of the code. You may have fixed a floating point issue and just shifted and turned it into a memory access issue, and now your code is slower. So you have to test everything. Don't profile with tiny cases just because they take 2 seconds, right? I do it here just to show you the screenshots, but if you do that and you're profiling a case that is not typical of your workload, you're not profiling the right thing, because you're not getting the right patterns of access to L2, L3, and main memory. So remember to profile typical cases. Remember to profile long enough that you're beyond the initialization period of your code, which might have a completely different behavior than the actual execution part. Because some codes have a first part that is initialization, perhaps setting up a mesh or doing a subdivision of a mesh and an assignment. That can take some time. If all you measure is that, and all you optimize is that, the main part of your code is still left unoptimized. Remember to add optimization flags. Since you're going to have to add -G, make sure that's the first flag in your compile line, not the last one. Otherwise, you might get an unoptimized code, and anything that you measure is really not very relevant. And remember to test for scalability. The fact that you can run on 16 or 32 cores efficiently does not mean you can run on 512. It doesn't even mean you can run on 64. So choose a case that doesn't take very long to run, and look at your scalability. Run at a point where your scalability is still good. Otherwise, you're wasting a lot of your own service units, and you're not going to get as much work done as you could. The do nots are very simple. Do not assume every change is an improvement. I think all of you are probably well aware of that. But don't profile a typical cases that are corner cases. That's not your main workload. Why would you profile that? I mean, unless you have a very specific reason to do it, don't do it. And put yourself a limit in how long you're going to spend on profiling and optimization. At the end of the day, all this is designed to do is make sure that you can run your jobs in a reasonable amount of time. As soon as you can do that, there's really no need for you to continue working on this unless you're doing it for a job or because you enjoy doing it. There are other tools that I haven't mentioned. Background is not really an optimization tool, but it's so useful that I like mentioning it anyway. It's mostly a memory debugging tool. MPIP is a lightweight MPI profiler that we don't have working in Stampede, but it will tell you which lines of source code make the MPI calls that take the most amount of time in your execution. So it's extremely, extremely useful. Now, Scalaska is similar to Tau and HPC toolkit. I've had more luck rebuilding codes with instrumentation for Scalaska than for Tau, so I very often use it as a substitute, and it's available in Stampede if you want to use it. And that's pretty much all I had for you today. So thank you very much. If you have any questions, you have my email on the slides, so feel free to get back to me with any issues if you're trying any of this out in Stampede. Thanks. Take away.